Good evening, everyone. We are just about ready to get tonight's Advent of Code live stream started. We are going to be solving Day 14's puzzles in C++, as we always do. Thank you to everyone tuning in to the live stream on Twitch, or if you're watching the replay later on YouTube. You can always find replays of all of our sessions for each day's puzzles on my YouTube channel at youtube.com/spoonboy42. And as always, you can find the code for these solutions up in my GitHub repository. That's github.com/Craig-Chasseur/AOC2020, which you can see on the screen right now. And as always, links down in the description. So last night we had what was for me the most challenging puzzle of this year's Advent of Code so far. It involved a lot of modular arithmetic, implementing the Chinese remainder theorem, which I did not remember too well. I had to, look it up on a wiki and, see what I was doing and tinker around with it until we finally got a solution. I think that kind of as I predicted, we are getting into some of the more algorithmically tricky puzzles for Advent of Code now that we're past the halfway point, and tonight going into Day 14. So we'll see what we have this evening. I mean, we might have another really challenging one. It might stump me for a little while, but I'm going to do my best here, and I hope you all enjoy following along with me as I try and figure out these puzzles. So right now we have a little over 5 minutes until tonight's puzzle unlocks. You can see that we are bouncing around this map on our Advent calendar. We've started going back north on our little map here. Yesterday we caught our bus that will hopefully take us to the next airport on our quest to go on a nice tropical vacation. But I have a feeling our route is going to continue to be pretty circuitous before we finally land on our vacation on Christmas Day. So in these few minutes before we have the puzzle unlock for us, I'm just going to go ahead and, as we do every night, set up the little scaffolding of our next day's solutions here. Say make a directory for Day 14 in our code base, and make part1.cc, which will be the source code for our solution to part 1. We'll make our usual minimal C++ program. You know the drill by this point. And we'll make a build file so that the Bazel build system which we're using knows how to build it. Okay. Now let's go ahead and compile and run that just to make sure everything's going okay. Okay, and no output as we expect. We might as well, while we've got a little time before the puzzle unlocks, go ahead and include the libraries, which we almost always use, which are our check library and our IO library, because we're almost certainly going to have to read our puzzle input from a file, and we'll have some assertions that we need to check. So we'll put those in as well, and put those in our dependencies for our solution executable. And it should still build and run fine. Yep, there we go. So we have about 2.5 minutes left. As always, if you have any questions, feel free to drop them in the chat, or if you're watching the YouTube stream replay later, feel free to leave a comment, and I'll do my best to answer them. I did get one comment on the stream replay from last night's YouTube stream asking about the build system and where I learned to use it. Bazel is the open source version of Google's build system that anyone can use. So I use it all the time at work. I first learned it when I was an intern at Google as a student. But, I like that it is fully declarative. It, only does exactly what it needs to do for exactly what's changed, and it caches its outputs well. It does really well with, defining custom actions that can define additional code and additional artifacts that might be a little more difficult to do in a makefile-based system. The one area where it is not totally awesome is configuring and managing optional external dependencies that you just expect to be already installed on the system and that aren't necessarily under source control and aren't built by Bazel. So another build system like CMake might do a better job with that, but overall, especially when you control and you build all the dependencies, I think Bazel is really great, and I'm a pretty big fan of it, especially for dealing with C++. So we have a bit under a minute until tonight's puzzle unlocks now. And I'm just wondering what it's going to be tonight. Hopefully it is not another tricky modular arithmetic problem where you might find me staring at the screen just trying to think about it again for a long time again. But we shall see. Just waiting for the unlock. All right, and away we go. As your ferry approaches the seaport, the captain asks for your help again. If your system runs the port isn't compatible with the docking program on the ferry, so docking parameters aren't being correctly initialized. For a brief inspection, you discover that the seaport's computer system uses a strange bitmask system in its initialization program. Interesting. Okay, so we have to emulate the decoder chip in software. Fun, fun, fun. So the initialization program can either update the bitmask or write a value to memory. Values and memory addresses are both 36-bit unsigned integers. 36 bits. I think some old IBM mainframes had 36-bit words. Write the value 11 to memory address 8. Okay. Bitmask is always given as a string of 36 bits, written with the most significant bit on the left and the least significant bit on the right. The current bitmask is applied to values immediately before they are written in memory. A 0 or 1 overwrites the corresponding bit in the value, while an X leaves the bit unchanged. Okay. So this program starts by specifying a bitmask. Mask specifies will overwrite 2 bits in every written value. Okay. Value 11 to the memory address 8. And okay, so these values here are decimals. Okay, so we're doing some bit twiddling, something that I am pretty comfortable with. To initialize the docking program, you need the sum of all values left in memory after the initialization program completes. The entire 36-bit address space begins initialized to the value 0 at every address. Okay. All right. So the entire 36-bit address space is going to be, I mean, that's can be 64 gigabytes, or no, if each word is individually addressed, it's going to be even bigger than that. It's going to be real big. It would be 64 gigabytes. It would be 64 giga words, and each word is 36 bits. So obviously we are not going to populate that whole thing. We're going to consider it to be sparse memory. And we will put it in some kind of map, I guess. So let's look at our input. Okay. So, let's make a struct to represent the mask, because what we're going to need to do is really the mask, each position in the mask can have three possible states. It can be the X for the pass-through, or the 0 or 1 that sets things explicitly. And we will use uint64t, which will have enough space to actually represent what we want to represent. And so we will say just looking at so we'll say keep bits are the ones that are X's that leave it unchanged, and then set bits are the 0s and 1s that we actually need to alter. So we will write a parse mask routine, which takes a string view, which will be a sequence of 36 characters. So just check that that is exactly 36 for the 36 bits that we're going to be putting in. And then we will start with our first bit position, which is 1, because we're going left to right, so we'll just shift what we have in both parts of the mask left for every additional character in the bit mask that we parse. So we will pass equals 1 to start with, the least significant bit, and we'll say mask parsed, and both the keep bits and the set bits will be initialized to 0, and then so for each character in the mask string, we will switch on the character. So if it is X, that means that we actually, for each iteration of this, we are going to I don't think we need to keep that parse bit. What we need to actually do is just shift everything that we've already parsed left by 1 when we're shifting in a new least significant one, and then we can just OR in the 1 bit. So okay. So if we hit X, then we need to put a 1 in the least significant bit of the keep bits. Now, if we hit 0, Well, we need to put a 0 in the least significant bit of the set bits. Now, we are not going to have a bit in the keep bit, so it'll just go to 0 anyway. And we don't actually need to do anything. We'll just break because, you know, this is an expected case. I mean, obviously, we could write, just for the sake of clarity, that we're ORing in a 0 there, but it really does not matter, because ORing in a 0 does nothing. It's a no. The compiler will probably optimize it away. And then for 1, we actually do need to OR in that least significant bit. And then if it is not one of those characters, then we will do our check fail because it's nothing that we recognize. So we have our mask parsing routine. And we'll call this other struct storeins to represent the parsed version of a store instruction. So we will say uint64t for address and uint64t for value, both of which should be parsed as decimal numbers. So So we'll use scanf here because the format is pretty simple. No, it should be... And then the string is the store line as a C string. The format will be mem and then unsigned long, which should map to uint64, at least on a 64-bit platform, and then another unsigned long format for the literal value that we are to store. So then we store the first one into the address, and we store the second one into the value. And the question is, it is not liking that. It says fix available. Can you quick fix me? LU, not UL. Just had those backwards, that's all. See, don't you just love ClangD coming through with those fixes for us? And then we'll make a little class called memory machine, where we will have a flat hash map to represent our sparse 32-bit address space. Because, again, you know, actually it looks like the memory addresses are all quite small, like they could even fit in 16 bits, but ostensibly these memory addresses could form a 36-bit address space. So I'm just assuming it's going to be sparse, and we will, you know, we'll plan for the future if we have to deal with big memory addresses in part 2. just default initialize there, and then we can just say, and we'll also remember the current mask. And we will have an exec store method with that store instruction that will actually change the contents of the memory. So to form the contents, let's see here. Okay. So we will take sparse memory at the address specified by the store is going to equal the keep bits of the current mask bitwise and with the value from the store. So so we'll keep all the bits that it tells us to keep, and then we are going to bitwise OR that with the explicit set bits from the current mask. And then finally, what we need to do to get our final result, the sum of all values left in memory after it completes. So we just need to sum everything in the values in that sparse memory. So we will do just iterate through that sparse memory and sum up all of the values in those pairs. And I believe now, oh, we need to do a little more parsing actually. Need to just write a little more I/O, so we'll say make sure that the argc is 2, and we get 1 argument to the program that represents the file name. Just string, thank you. Make sure we include vector and string here. Nope, that's not what I meant. So read those lines from the file. We will start up a memory machine. And then for each of those lines, we will parse it. So we'll just say if the line starts with value, oh no, it's not value, it's going to be mask equals, then what we need to do is we will say the mask string is going to be is going to be the substring of the line starting at character 7, because it's going to be 1, 2, 3, 4, 5, 6, 7, and then we will start getting those mask characters. And actually, we can just feed that parse mask directly into our memory machine. So I'll say machine.setMask and do that straight away. Now, otherwise, we expect that the line will start with mem and look like a memory store instruction. And if so, we will go ahead and pass the parsed version of the store instruction to our memory machine. And then the else here, every line should be either a mask or a store instruction. So we'll put a check fail in the else case here. And then finally, we will spit out the sum that of all the values in memory that the memory machine gives us. So I think that is all we need. We're just going to need to add dependencies on flat hash map and strings to our program here. So got the stuff that we used from the Abseil library, and I'm just going to get the very simple example program from the website and use that as a little test program for us here. And it gives us that is not correct. So only two values in memory are not 0, 101 at address 7 and 64 at address 8, producing a sum of 165. So how about while we go through this sum memory, we go ahead and give ourselves a little debugging information and say mem value.first for the address. Just see what it thinks is going on here. So it thinks 7 is 101, which is correct. It thinks 8 is 0, and that is not correct. So I mean, it does recognize that we tried to store something to 8, and initially we would have tried to store 11 to 8, and then are we not applying the masks correctly, I guess is the question. Let's look at the stores then, I suppose. look at what the set bits are, because I'm a little suspicious about that. We always did keep bits in all of these, and we should have done set bits. That is exactly what we did wrong. It was just me being a little hasty in the parsing routine. I bet when we run it this time, yep, we get 165, which is the correct answer. So just, you know, a little careless in writing that routine up there, but I think we are good now. So now let's run this for our actual day 14 input. And we get that value for all the memory that we sum up. Let's see if we are correct. All right, on to part 2. It must be using version 2 of the decoder chip. Version 2 decoder chip doesn't modify the values being written at all. Instead, it acts as a memory address decoder. Oh, we got ourselves an MMU here. Immediately before a value is written in memory, each bit in the bit mask modifies the corresponding bit of the destination memory address in the following way. If it's 0, it's unchanged. If it's 1, it's overwritten with a 1. If it's X, it's floating. A floating bit is not connected to anything and instead fluctuates unpredictably. Practice means the floating bit will take on all possible values, potentially causing many addresses to be written at once. Phew, boy. My goodness, this might be kind of tricky. Because I don't think that we're actually going to be able to populate everything that is floating. So, if I look back at, these floating bits are going to be an issue because I have a feeling that some of our masks are going to have so many floating bits that it's going to be impossible to actually emulate that whole address space, and that is going to be what is tricky about this problem. So, you know, actually, let's just, well, okay, first thing I'm going to do is copy our solution from part 1 over to be our executable for part 2 that we'll start with. Now, the first thing I want to do is just find out a little bit about our input, find out what the largest number of floating bits which will be set in this are. So we'll say we'll change keep bits to floating bits. Exec store is not going to work the same way, and we might need to change our sparse memory representation. But what I do want to do here is just comment out a bunch of stuff, like everything having to do with the machine. The only thing that I really want to do here is I just want to see what are the number of floating bits that we have for each of the masks that we parse. And that will kind of maybe give me an indication of how feasible it is to actually like brute force filling out the memory, or if we need to do something more clever. So I'm just going to use the built-in sorry, built-in pop count. LL, or just L, should, no, I'll just do L, I'll just be safe. On mask stir dot, or not mask stir, it should be stir dot floating bits. And let's just see how big these are. And we also have to make a build target for part 2 before we can do that. Same dependencies. Let's run part 2 and see. Okay. The highest number of bits that are set is 9, which would correspond to 512 different addresses. And then, of course, you multiply this by, like, let's see how many actually, okay, there's 100. You know, I believe that there is a more clever way to do this. But I think that our current sparse memory implementation might actually still be okay for this. I don't think that it's terrible, to be honest. So what we really need to do is just change the implementation of exec store so that it stores to all the different addresses that can be specified by floating stuff. So let's see. The store, we will always store exactly the value from the store. We just need to figure out which of the addresses that it goes to. So this address base is going to be the address of the store ORed with everything in the set bits from the mask. So basically, if it's 0, if the set bit, if it's 1 in the, if it's 1 or 0 in the address base and it's 0 in the set bits from the mask, it will be 1, which is to say unchanged. Yeah, ORing with the set bits from the mask will leave the actual fixed bits of the address what we want them to be, I'm pretty sure. So, okay. Then what we need to do is for all of the floating bits, we need to compute all of the different possible values of the floating bits. So, and that's, you know, up to 9 bits that we'll be toggling every which way. So I'm just thinking about how we want to generate these addresses, and for, you know, for 9 floating bits, it'll be up to 512 different addresses for one of these stores. So I'm going to maybe make a helper function that says, called generate address. You know, this is crazy, but I think that there's actually an x86 built-in instruction for parallel bit deposit that does like almost exactly what we want to do. And I wonder if that will actually make this easier. So this is non-portable stuff, but this bit twiddling, you know, especially PDU64 deposits contiguous low bits from unsigned integers. Oh my, man, this could be it. All other bits are set to 0. Okay. I really want to try this. I think that they amazingly, like, using these low-level assembly intrinsics might just be exactly what we want to do, and I'm so tempted because, you know, I just know that they're built into the processor. This isn't necessarily pure C++, but if this works, I'm going to be really pleased with myself. So let's give it a shot. So we will include imm_intrin.h, and we will use the special BMI2 x86 instructions. So what we need to do is say int mask bits equals, and again we're going to use one of these built-ins. We're going to use built-in pop count to count up the number of bits in that floating mask. And so we basically just go from uint64t, so 0 for all of those bits, up to all of those bits being set. So that's going to be we'll call this floating bits contiguous because we're just going to be counting up all the numbers. Going up to floating bits contiguous is, so we want it to go up to, but not all the way to 1 shifted over left by mask bits. So what we're doing here is we're counting through all the numbers in that range. So these will represent all of the bit patterns if they're contiguous. So like if we had a floating bit mask that had 9 bits in it, this would count all of the numbers from 0 up to 511. So all the possible bit patterns of 9 bits on and off. And what we are actually going to use, the fancy x86 instruction that we're going to use is the PDEP instruction, so parallel bit deposit. We're going to use that floating bits mask, and we're going to scatter those contiguous bits so that they are actually at the bit positions specified in the mask. So Um, so for the floating bits, we will say pdep u64. The first parameter will be those contiguous floating bits. And the second parameter will be the actual mask that specifies what bit positions they get scattered into. And then we will just OR the result of that together with the address base, which has all the other set bits. So at that point, we have our actual address, and we can store the value into it in our sparse memory. So I think we can get rid of, let's see here. Yeah, we can get rid of these. I think we might actually have our answer here. So the first thing I'm going to do is take the example program for part 2 from the website and go ahead and use that as another test. And so if we run our part 2 on that particular test, okay, we got a problem here. Oh, okay. So I think we just need to change our compilation options. So that we compile for the actual architecture of my machine, which is a Skylake machine, which does support those BMI2 instructions. Oh, so close. It says, in this example, the sum is 208. And we got 202, so we're doing something wrong. Okay. Let's, for each of these stores, we'll just have it spit out the address and see if that looks like what we would expect given our test input. Let's debug this a little bit. Okay. So that initial program saying 58, 59, okay. So it really should be going to 26, 27, 58, 59, then 16. Okay, so something about this math is not quite correct. Something about our address calculation is off. Let's see here. I mean, we have the right number of stores. Let's look at address base. Now address base is 58. That's not correct. That should be 26, and it has that high 1-bit set. So you know what? I think it's just a matter of and, not or. You got to be tricky. So let me run this through again. Yep. Oh no. Okay. That ultimately got us the right answer, but it is still not correct where this ultimately is. So I think it's just calculation of the address base that we screwed up. So let's work through these instructions again and see how the address base should actually be formed. So if we have an X, we're going to have 0 in that position for the set bits anyway, and it will get overwritten with some of the floating bits. If the bit mask is 0, the corresponding memory address bit is unchanged. So, and if it's 1, the corresponding memory address bit is overwritten with 1. So, I mean, that really makes me think it should be an OR, except that, let's go ahead and print these out. Sure, I'm missing something simple here. I actually think the fancy stuff with parallel bit deposit is actually all good to go. We just need to figure out the simple part in calculating the base address that we're going wrong with here. So we'll say okay. Test stream modifier we can put in there. Not sign. Bin. Nope. I'll put them in hex anyway. We need to zero out some bits from the store address is the problem. That's what's going on here, because we need to, you know what, we need to AND this with the inverse of the floating bits. And I think that should do it, because the floating bits should all initially be zeroed out, and then we'll toggle them. There we have it. Yep. Yep. We were just I was thinking only about the bits that are covered by the set bits, and not thinking that, you know, all of the bits covered by floating bits have to initially be zeroed out. So I think we actually have an answer, have our program ready to go here. At least it gives us the correct output for that test input. Let's see what it does for the day 14 program. Okay, this is what we have for the sum of our memory. Let's see if we got it right. All right. Another successful one. Let's see where we were on the leaderboard. Okay. You know, under 2,000 for part 2, just barely above it for part 1. Pretty successful day. Did not get nearly as stumped as I did last night. I think bit twiddling stuff is much more in my wheelhouse, although you still did see me make a few mistakes. But, you know, going through this, I think part 2 of this, oh yeah, Woot in the chat, thank you! Going through this, I think the one thing that tripped me up really was just informing this address base. I screwed that up a little bit initially because I was really only thinking about the bits, the zeros, and, you know, matching the zeros and ones with the mask. But I wasn't thinking about the fact that all of the floating bits had to be initially 0, and then we would twiddle them with zeros and ones here. I think that, you know, I used this PDEP instruction, which is a proprietary Intel instruction, although I think it is supported on later AMD CPUs as well. But it's just, I knew that the x86 processor had this instruction, and that it would, and that we would be able to do that, use that to do exactly what we want. In the chat, we have some comments. It's much less mathy. Only downside of solving it in C++ is you don't get to play with recursive generators. I suppose so. You know, we definitely could have. I was initially thinking about writing a recursive implementation of the address generation function. PDEP is not undocumented, though. I mean, it's all there in the Intel architecture manual. In fact, I will even link in the chat right now the Intel Intrinsics Guide, which is very useful for having all of those intrinsic instructions for x86 processors. Now, if I were to make this fully portable, I would do something different. That, you know, we would, you know, just scan through the bits, and, you know, when we found something that was toggleable, we would flip that. But honestly, I mean, how often do you have a single assembly instruction that just perfectly matches the semantics of what you're trying to do? So I enjoyed the chance to use that. I enjoyed having fun with bit twiddling. You know, I was a little bit worried. You know, we have this sparse memory model here, and like I said, in our puzzle input, the maximum number of floating bits that we ever had in a mask was 9, which corresponds to 512 different addresses. So the memory use of this sparse memory map is not going to get totally out of control. Although I do think that there is something that's possible where you could possibly think about. It could possibly track how many copies of a particular store you know to be live in memory, and then do some sort of collision detection algorithm between the bitmaps without having to store every word separately. But this ran plenty fast enough, as we saw. So once again, thank you to everybody on the stream watching us solve this problem. Thank you to everybody tuning in later, watching the replays on YouTube. As always, you can find the stream replays on my YouTube channel at youtube.com/spoonboy42. You can always find the code for these solutions up on my GitHub repository here. I'm putting that on the screen now. github.com/Craig-Chasseur/AOC2020. Thank you to everybody joining the stream tonight. Thank you to everybody who's watching this later. I had a lot of fun with this one, and I am really looking forward to what we see in the days to come with more of these puzzles. So please come back, watch the stream again, watch the replays again. I will see you all tomorrow night. Have a good one, everyone.